Thank you very much. Well, thank you very much for the invitation, first of all. So, the purpose of this series of lecture will be to present a setting to, well, I should tell you a general setting. For quantization. And here I should say immediately that quantization for me means deformation quantization. So everything I will use the word quantization always means deformation quantization. And we will see some examples in a minute. And the interesting thing about this setting is that it gives first another point of view on, say, well-known examples. So that's, say, new point of view on well-known examples. So typically it will give a new point of view on quantum groups, for instance, where new, in some sense, quantum groups. It also gives a kind of new point of view on symplectic reduction, for instance, this kind of thing. And maybe more interesting is that this general setting allows for introducing many, many new examples. So there will be many new examples of deformation quantization. Okay, so maybe to start with, so today I will present some, motivating examples. So I will just make comments about 3 situations to try to explain where we are going to. But maybe before that, let me present a theorem, and the purpose of the series of lectures will be to explain this theorem. So I don't expect you to understand the statement because there will be unexplained words, but I will explain these words in the next lectures and try to give you an idea of how it is proved. Okay? So let me state this theorem and keep it in mind as the main goal of the series of lectures. Okay. So I start with G, a reductive group, and everything is going to be over some base field of characteristic 0. So varieties will be algebraic varieties over K. Reductive group is an algebraic group over K, which is reductive and so on. Okay. Suppose that we choose a G invariant scalar product on little g, the Lie algebra of G. And suppose that I have a X, which is an oriented space. So I'm not going to make this clear at the moment, but I will give you 2 main examples of what an oriented space means here. So first, it can be a compact oriented topological manifold. E.g., that can be a compact oriented topological manifold. Or it can be an algebraic variety which is oriented in the sense of algebraic geometry, which is a Calabi-Yau variety. Give me a smooth, projective Calabi-Yau variety over K. And let's say that it has a dimension D. So either the dimension as a manifold or the dimension of as an algebraic variety. Then the statement is the following, that the moduli space Bun-G of X of G bundles on X so if X is a topological manifold, I really mean by G bundles on X, like flat G bundles on the manifold X. And if X is an algebraic variety, I mean algebraic G bundles on X. And this is where it starts to get a little bit cryptic. So this module, sorry? You said flat bundles? I said flat bundles. In this topological case here, by flat bundles, I mean representation of the fundamental group with coefficient in G. Okay. And so the moduli space Bun-G of G bundles on X suitably considered as a derived algebraic stack. So this is one of the words that I have to explain. I won't explain this today, but tomorrow. Admits a canonical n quantization. This is another word that I have to explain. And here n is an integer that is related to the dimension of the variety by the following formula. It's 2 minus d. Okay, that's the main theorem we are aiming to. And hopefully at the end of the 3 lectures, you should be able to understand all the words in this statement, and also to have an idea how it is proved. Okay. So I'll explain these words tomorrow, and I'll explain n quantization in the third lectures. And today I will give you 3 instances where this quantization can be identified in some specific examples for X, to just that will serve as motivating examples and to try to explain the kind of statement that is behind this theorem. So today, 3 motivating examples. Okay, so the first thing is that X can be a point. So D can be 0. So then I'll comment about the moduli space of G bundles on the point a little bit later. But this quantization here in this setting is something known as the quantum group. So here we have the quantum group. So I start with rep G, the category of representations of G. And I look at it as a tensor category. And the quantum group is a deformation of this thing. So I don't know what's the notation, maybe Not sure this is really standard. I don't know. It's a deformation of the category of representations of G as a braided monoidal category. So this thing is a linear category, so it's a category over K, and it's symmetric monoidal. And this one is a category over formal power series over K. It's not symmetric monoidal anymore, but it is braided monoidal. And if you fix the parameter being equal to 0, you find back this category of representations. So when X is a point, I'll discuss a little bit later what is this, but the n quantization, so the 2 quantization here, is this quantum group. And this integer 2 here is related to the braiding here. Because, well, I explain this later, but there is a precise relation about the fact that we have only a braided monoidal category and the fact that the integer is 2. Okay. So in this case, the theorem is just another way to state the existence of quantum groups. It's nothing more. Okay, so second example is when X is of dimension 2. And I will be more specific. I will assume it's a compact-oriented topological surface. So let's say that X, I will call it sigma. Are there some questions?
We don't know what braided is.
Okay. Well, I will come back to this in the third lecture. So, so when you have a monoidal category, you can impose different symmetry constraints on the monoidal structure. You can just have a tensor product without any condition that just associativity, but you can also assume that X tensor Y comes with an isomorphism with Y tensor X, and depending of how this isomorphism behaves. So, for instance, if you compose it 2 times, if you find it the identity, it means it's symmetric. But sometimes, if you compose it 2 times, it's not the identity. And the relation that this isomorphism satisfies are given by the braiding relation. Okay. So there is an action of the braid on the. Typically, braided means that if you look at the n power of X, there is an action of the braid group of n with n strings on this object here. Okay, you can switch the factors. Okay. So this is what braided means. And so maybe I use the opportunity to make a little bit more comment about this. So, okay, so typically when you have a tensor category, it can be something called E1 tensor, which is just associative. It can be E infinity tensor, which it means symmetric. And it can be E2 monoidal, which is braided. So what we will see is that there is a hierarchy of commutativity constraints you can put on tensor products. Here, I work with categories, so you have only 3 possibilities, associative, braided, and symmetric. But we will work in a setting replacing categories by some infinity categories where you have En monoidal for any n. And this is where this n comes from. Okay. Does it answer your question a little bit? So braided means it's a little bit symmetric, but it's not fully symmetric. Okay. Yeah, so I assume that X is a compact Riemann surface now. So there is an incarnation of this moduli space. Again, I'm not going to discuss these derived algebraic stacks yet, but there is something you can construct, which is the character variety. I can look at the character variety of sigma with coefficient in G. That's an algebraic variety. It's an affine algebraic variety. It can be explicitly constructed by you take the variety of Helms from the fundamental group of the surface to G. Okay, this is given by some. This is an algebraic subvariety in some corner of G, and you divide by the conjugation action. It's called the character variety. Of sigma in G, say. And this is an approximation of what this moduli space of G bundles on X is. Well, you can take this as a definition. It's not quite what I mean in this theorem, but it's pretty close to be what I mean in this theorem. So it's an algebraic variety, and the points in this algebraic variety parameterizes flat G bundles on the surface in the sense they parameterize representation of the fundamental group with coefficient in G up to isomorphisms. So that's an approximation to this Bern G of sigma that appears in the theorem. So I want to keep this. So let me erase here. Now, as it is an affine algebraic variety, it has a ring of functions. So I can look at functions on this character variety. That's an algebra. It's a commutative algebra over K. And it's something well known in topology, that it has a canonical non-commutative deformations. There is a natural non-commutative deformation of this ring, of this algebra, called the Skein algebra. I'm not completely sure about the literature here, but when G is SL2, this is really called the Skein algebra, and it has some presentation by generator and relation. It's rather explicit. But it's directly related to a deformation quantization of a natural Poisson structure on this guy here. So a way to see it, a way to see this deformation I will come back to this later, actually. Let me just state this. So there is a canonical thing identified as the Skein algebra. And it's a non-commutative deformation of this ring of function. And this is exactly this zero quantization we are talking about. So here n is 0, and the zero quantization of this Bern G X, which is approximated by this algebraic variety here, is, well, as this one is only an approximation, this is also only an approximation of what it really is, but it's a good idea of what it is this deformation. So it's not, so for quantum groups we have seen that it's a deformation of a monoidal category. Here we have a deformation of an algebra. We have a commutative algebra, and we deform it into an associative algebra. And the output of this theorem in this situation is essentially this non-commutative deformation. Okay, so that's for dimension 0. Not quite. I will make a comment. You have a deformation of a category, really. You want to think of this as you look at modules over this algebra, and the deformation gives you a deformation of the category of modules. So that's really the canonical way to think about it. But you can think of it as a deformation of algebras of functions on something. Sorry? It is associative. It's associative unital, but it's not commutative. Yes, but there is a difference between associative on the level of the category and associative on the level of algebra. So if I have an associative algebra, modules over this thing has no tensor product, so it is E0 monoidal. So there is a shift between the tensor product on the category of modules and the commutativity constraint on the algebra itself. Okay, so it's if you look in terms of categories, this is really E0 monoidal as a deformation of categories. Well, I'll come back to this in a minute. I will make these comments. Okay, now let's say something about dimension 3. And let's take this case just to change. So I will assume that X is an algebraic smooth projective Calabi-Yau variety of dimension 3. And, well, again, this guy in the theorem is approximated by some moduli space. So there is an approximation by a moduli space. Let's say, I don't know, M of maybe stable G bundles with fixed numerical invariance. These are not really. So if I look at G bundles on X, it has many, many components. It's very big, so you have to fix like the Chan classes of the G bundles to restrict to a smaller space. And then stable G bundles are nice ones for which you can construct a moduli space. But these are not really. This is not really important for the example here. You just suppose that this is a pretty complicated object, and it has an approximation which is just an algebraic variety whose points are in 1-1 correspondences with some nice G bundles on X. Now, it's known that M has a very particular local structure. So it's locally of the form critical locus of a potential. So here, f is a function. So it's an algebraic function on a smooth variety. C is smooth. It's a local smooth ambient space containing M. And M inside Z is just the critical locus of this function.
Z is finite dimensional.
Z is finite dimensional. And this is only a local picture, okay? This is not true globally. But locally, say, in the Taritsky topology, this is known.
I'm not understanding these dimensions here, because the previous case was a Riemann surface and was equal to, so I thought it was the real dimension. And here you are talking about cover-up.
Yeah, the dimension here depends on, it's really the dimension of the, what counts here is the dimension of the orientation, okay? So here the fundamental class live in dimension D, or the topological dimension. Here the fundamental class is, this is oriented in the algebraic setting, so this lives in dimension D, but D is the dimension of, as an algebraic variety. So if you have an algebraic variety over the complex numbers, you can also look at it as a topological manifold of dimension 2D, but that's a different story. This is not, there is a difference between the moduli space of algebraic G bundles on X and flat G bundles on the underlying topological manifold. These are two different things. Okay? So what really counts is the dimension of the orientation in the sense of cohomology. Where lives the fundamental class?
So in the previous case, if you had considered tori, and you had gone through the down arrow, it would give something different. In the case of Riemann surfaces, if you consider a tori.
Yes. You mean an analytic curve? Yeah, then n would be 1. That's something completely different. Take G bundles on an analytic curve. It's the case n equals 1. I don't discuss the case n equals 1 here, but it will be a different story. And the moduli space underlying these things are not the same, just not the same. Okay, it's a moduli space for all kind of G bundles on the elliptic curve, maybe not flat ones and so on. Okay, so it is known that locally it's given by such a thing. This is actually a theorem which is not completely. It's due to Joyce and co-authors, and it's not the fact that it is true locally for the Zariski topology is not something obvious. But anyway, it's known. And let me back. I will erase this now. So there is something you can do when you have a function like this, and you have the critical locus. On the critical locus, there is a sheaf of vanishing cycle, essentially. So on the critical locus of f, there is a particular, well, it's really a perverse sheaf, so a sheaf of vanishing cycle. Nu of f, which tell you something about the singularities of the fiber at 0, say, of this function. And under some condition, I mean, in some examples, you can glue these local constructions. So this local construction can be glued where under some condition, which I'm not saying the conditions here, it's again something of Joyce and I don't want to discuss the details here. And they glue into a globally defined sheaf. So you get E, a sheaf, on M, which locally looks like vanishing cycle for a given potential. Now this sheaf E can be understood as a deformation. So it's just a sheaf of vector spaces. It's not like a coherent sheaf or even a complex of coherent sheaf. It's really just a sheaf of vector spaces. I assume that we are over the complex numbers, and I'm just saying that there is a sheaf on the underlying topological space which is constructible in some sense. Okay. And as such, it can be understood as a deformation of some crazy guy. Something like this, which is the virtual half forms. On N. Okay, let me not go into details here. So there is something which looks like, this looks like a line bundle on M. It's not really a line bundle, but it looks like more a complex of vector bundles. And it can be deformed as a sheaf of vector spaces. And this deformation is this E here. So this E, again, is a deformation quantization of something. And maybe as a comment, I should say that if you take the Euler characteristic of M with coefficient in this sheaf E here, this number is what Donaldson-Thomas invariant of X is. So these are the dt invariant of X. So this E is a categorification of these numbers associated to three-dimensional Calabi override. So now the difference between the two other examples is that there is no really deformation of a category here, but there is a deformation of an object in a category. Still, this is compatible with what we have just seen. Okay? In any case, the output of the theorem is essentially the existence of this E, which is a deformation of something that naturally lives on M. Okay, so maybe let me discuss now the similarities between these examples. And
can you say something about this function? Or?
Well, you just know that they exist, and they are not far to be unique. If you put enough structure on M, they are not far to be unique. But it's not, I mean, well, this is something I don't really know about, but you want to look at it, you want to think of it as an algebraic analog of the Chan-Simon function or something like this. Okay. But as you work algebraically here, there is no such a thing. So you just know that locally there is one. I'm not sure that they are explicit, but you know that there is one. If you put enough structure on M, it's more or less unique. So, I mean, the non-uniqueness is controlled. I mean, in this work here, there is this under some conditions that are exactly the conditions you need to be able to glue these local constructions, which is related to the fact that the potentials might not be unique, but how non-unique they are is understood.
The deformation parameter is a geometrical interpretation?
No, it's just a formal parameter.
So it's just that it appears in I mean, I guess this shift will depend on some deformation.
Yes, so I'm going a bit fast here. So this is in this case, I think this is more than just a formal deformation, it's an actual deformation. So this is the value at h bar being 1 of the formal deformation. But now you can look at, so this is like a perverse sheaf. So it looks like the sheaf of solution of some algebraic differential equation. And so there is suppose that you have like a vector bundle with a flat connection. You can write down the Derived complex, okay? And you can multiply the Derived differential by a small parameter. That's the deformation you get. So when h is 0, you just get the forms on your vector bundle, which is more something like this. And when h is 1 is what you get, okay? But here, yeah. Well, the parameter really multiplies a differential in some complex. Okay, so some comments, so some similarities between these three examples. I want to try to explain that they are the same kind of phenomenon. I mean, they are just the same thing. So in all of these examples, there are underlying moduli spaces. Well, it's pretty clear for example 2 and 3. Here you have the moduli space of G bundles. In example 2, it was this character variety, which is an approximation of the moduli of this Bun-G. Again, it's something that can be thought as the moduli space of flat G bundles on the Riemann surface. But for example 1, it was not completely clear. So let me start with this. So I said that X is a point. If I look at G bundles on a point, of course there is only one, which is a trivial G bundle. But this G bundle has a lot of automorphisms. Namely, G itself. So G is the group of automorphism of the trivial G bundle on the point. So the moduli space, let me not use the word space, the moduli of G bundles if you want to construct it, well, there is only one point, which is a trivial G bundle, but this point comes with many automorphisms. So it's something like a point where G acts trivially. Okay? And if you think in terms of, you want to think of this thing as a groupoid, that has a name, it's called BG. So it's a non-trivial structure. It's not only just a point, it's a point where G acts trivially, but G acts. So that's an example of an algebraic stack. So we will come back to this in the lecture 2. This is an example of an algebraic stack. It's a quotient of an algebraic variety, which is the point here by an action of an algebraic group, which is G. And the correct moduli of G bundles is really this thing. It's not just a point. Now, the interesting comment is that if I take vector bundles on this moduli space, so vector bundles on the point is just a vector space, but now I really want to keep track of this action of G, so I really want to look at G equivariant vector bundles on the point, which are nothing else than the representations of G. So if I look at vector bundles on BG, this is rep G. Or instead of vector bundles, I could take coherent sheaves. It doesn't really matter. Here, these are the same. So rep G here appears as the category of sheaves on the moduli space of G bundles on the point. Okay, that's the comment I wanted to do, is that rep G, this is just coherent sheaves on, say, burn G over the point, which is this algebraic stack BG. Now, then this picture is also true for the two other examples, in the sense that the quantization, as I said, is a deformation of this category. And the two other examples are of the same type. So let me discuss example 2. Where there is also a moduli space, you can also look at coherent sheaves on this moduli space and look at the deformation consider it as a deformation of the category. It's a deformation of the category of sheaves on the moduli space of G bundles. I just don't have a watch, so can you just tell me what time is it? Sorry.
So you have 20 minutes.
20 minutes. Okay, so what's happening in dimension 2? So X was a compact Riemann surface here. And as I said, this burn G of sigma, up to some approximation is this algebraic variety here. And this corresponds to a ring of functions. Now, I can identify coherent sheaves on this variety with modules over this ring here. So I have an equivalence between coherent sheaves on this algebraic variety and modules, or maybe finitely generated modules, and I can just take quasi-coherent sheaves to get all modules. Doesn't really matter. And then there is this deformation here. I said that this skein algebra is a deformation of this as an associative algebra, so it deforms the category of modules into another category. I didn't give a name, but let me put a little q, say. Mod. So modules over the skein algebra. So it's again the same type of situation. We have a moduli space for G bundles. We have the category of sheaves on it, and we have a deformation of this category of sheaves. This is now just a deformation as categories. So this is a deformation of categories without any monoidal structure, without a tensor product, okay? This is just an associative algebra. There is no tensor product on the category of modules, just a deformation of categories. Here it was a deformation of braided monoidal category. Here it's a deformation of just categories without monoidal structure. So without monoidal structure, you want to think of it as E0 monoidal. And this is where the 0 comes. Okay. And the example 3 would be a little bit too complicated to explain now, I think. So maybe we will be back to it at the end of the lectures. But there is also a parallel story in example 3, but it's getting more evolved. But you can still make sense of a certain moduli space of G bundles on X, a certain category of sheaves on this moduli space, and an object in this category that has a deformation, which is this sheaf E I was talking about. So I won't be very precise here, but there is a certain category of sheaves, say Q co on this moduli space, M. There is a certain object in this Q co and a deformation which is this E. It's not a deformation as a quasi-coherent sheaf, but it's a deformation as a sheaf of vector spaces or a complex of sheaves of vector spaces. So it's again the same kind of story here, but we don't deform the category itself, we deform an object in the category. But still, it has something to do with sheaves on the moduli space. So we can already extract something from these similarities, is that the n quantizations of the terminology n quantization in the theorem refers to a deformation of the category of sheaves on the moduli space of G bundles. So that will be a first conclusion at n quantization. If I come back to the statement of the theorem at the beginning, these really mean a deformation of the category Q co Bungie of quasi-coherent sheaves on this guy here, and the integer here, as we will see, that the correct notion is that it is deformed as an EN monoidal category. That has to be explained. I mean, it's not something I explain here. But we see in these examples when n is 2, 0, or -1. So E minus 1 monoidal means we deform an object somehow. That's what we expect now. So it clarifies a little bit the statement in the sense that these n quantizations are deformations of the category of sheaves on the moduli space of G bundles. And these deformations are deformations as monoidal categories with some commutativity constraint depending on the integer n. Okay. So we'll continue with the similarities to do a first step towards derived algebraic geometry. Or maybe there are questions.
How does example 3 fit into this scheme? Like,
Sorry?
How does example 3 fit into this scheme where you're deforming an object?
Well, it's related about what E minus 1 monoidal means. So there are two possibilities here. I will be back to this later in the third lectures, I think. E0 monoidal means you just forget monoidal structure, just look at categories. The natural thing for E minus 1 is just to say it's an object in the category, and E minus 2, it's a